Hi, good morning everybody. So, today I will talk on, I will continue to talk on this fast reactions, and in my last lecture I have talked about this flash photolysis. So, flash photolysis is a technique by which we can follow fast chemical reaction. It is one of the techniques by which one can follow fast kinetics. So, in that case a modern version of flash photolysis which is known as laser flash photolysis. So, in that case laser is used instead of a flash lamp, because lasers can deliver more intensity compared to flash lamp or maybe ordinary like these lamps. Okay. So, that is why flash photolysis is now replaced by, in most of the cases flash photolysis is replaced by laser flash photolysis, and in short it is LFP. Now, using this technique one can study fast kinetics, as I gave you example of photoreaction of benzophenone. So, when benzophenone gets excited with laser of say frequency 355, wavelength 355 nanometer. So, BP H nu BP star photo excited benzophenone. This photo excited benzophenone then it is a singlet one. Okay. Then it will move on to triplet. Now, this triplet benzophenone abstracts a hydrogen atom from another molecule producing benzophenone ketyl. So, H dot BP ketyl radical. Okay. So, ketyl radical plus another radical which is coming out of the other part, which is supplying this H dot. So, thereby it is generating a radical pair. Okay. Radical pair means a pair of radicals. Okay. Now, depending on the spin orientation, orientation of spins of this spin and this spin, this radical can have a singlet, parentage, or rather it may be singlet or maybe triplet. So, for singlet these two spins are like, and they are located on different parts, on one is on BPK, another is on R. Okay. And there is a finite separation between them. So, what will happen that when they may form a bond, when these two spins come to a bonding distance, they will tend to form a bond. Okay. Now, so therefore, this is the singlet one, and triplet one can have like this, but it will have, it is a threefold degenerate. Okay. So, I will come to that how it is threefold degenerate. Okay. Now, what is happening that if you do the experiment that is flash photolysis, okay, that is you shine your sample, maybe benzophenone, which is micellized, micellized within within SDS, sodium dodecyl sulfate micelle. So, when it is micellized, and then if you shine that micellized benzophenone with say 355 nanometer radiation, then this will happen, okay? And therefore, a radical pair is generated, okay? So, you know, these spins are electron spin, because of spin they are paramagnetic. So, the substance, that is the solution, will have some magnetic behavior, okay? So, in presence of an external magnetic field, we may expect something. What is that? That if you do photolysis in presence of an external field, say, you know, by means of a simple bar magnet, if you shine your sample in presence of, say, this is your bar magnet, okay? You just take your bar magnet close to the sample compartment, or maybe close to the cuvette, okay, and then you shine the radiation. Then some differences may be expected, okay? So, in my last lecture I was giving you the idea about the signal, that say this is the decay profile. Decay profile, that is as a function of time. Of course, this time scale is of the order of several nanoseconds, maybe even 2 microseconds, and this is your OD, or maybe delta OD as well. So, what is going on, that if you monitor your signal at, say, 550 nanometer, then you will be getting a decay of this sort. So, in presence of external magnetic field, B external is equal to 0. Now, you increase your magnetic field. So, if there is no effect, then if there is an effect of your external magnetic field, then you may expect that your decay profile will merge, new decay profile will merge with the old one. If there is no such, you know, radical pair formation, and their you know, dynamic behavior is not affected. By the term dynamic behavior, that how their spin orientation, I mean overall spin is you know, evolving with time. So, dynamic behavior means maybe it started with a singlet radical pair case, and ultimately it is converted to a triplet one, or maybe vice versa. So, that is, you know, with time their description, that is the description of singlet state to triplet state, or triplet state to singlet state, that may happen, okay. So, what has been found is that in presence of an external magnetic field, that is B not equal to 0, that is, you are applying some external magnetic field, maybe static magnetic field, it is found that it is like this. So, the decay kinetics, decay of your this BPK, because you are monitoring your ketyle at, say 360, I mean 560 nanometer or 550 nanometer. So, decay kinetics is found to get altered. So, why this is happening? Why I mean, in presence of an external magnetic field, something is happening, so that this decay is getting affected. So, magnetokinetics is a branch of chemistry which is known as spin chemistry, where we deal with spins. Here we deal with electron spins. So, in presence of an external magnetic field, how this spin, I mean spin of an electron, its projection, okay, is, you know, getting affected in presence of an external magnetic field. How this is affected, and how this is going to alter the kinetics of the process. Kinetics of the process means, you know, maybe it is a back hydrogen transfer process, maybe back electron transfer process, or maybe other kind of recombination. By the term recombination, that you have, say, two radicals and they will recombine to form a bond. that is called the recombination. So recombination. Okay. So how this is going to, I mean, this process is going to be affected in presence of an external magnetic field, that we are trying to focus, and that is the you know main thing in magnetokinetics, that is effect of external magnetic field on kinetics, on the dynamic behavior of radical pair. Okay. And broadly speaking, here we are looking into dynamic behavior of recombination of radical pair. Okay. So we are just we just try to find out the answer. I mean, try to give you, I will just try to give you an idea, okay, an overview of the process, what is going on with these spins once these radicals are generated. Radicals may be generated by homolytic cleavage of bond, or maybe excited state atom transfer, maybe excited state electron transfer. There are various ways by which, you know, radicals and radical pairs may be generated. Okay. So it is a photochemical generation of radical pair. It is a photochemical means, that is, you shine your sample with photons getting excited, then this excited ensemble of, you know, molecules will do further reaction, maybe a cleavage of bond, homolytic, or maybe, you know, atom transfer, like I told here, this hydrogen atom transfer, or maybe electron transfer as well. That is, the excited ensemble may accept an electron from an electron donor, or maybe excited ensemble of molecules will donate one electron to another acceptor. Maybe it is in the, preferably it is in the ground state. Okay. So let's look into look into this. That is, we have got this R1 R2. It is a homolytic cleavage, okay, maybe producing a triplet radical pair via intersystem crossing. It may get converted to a singlet radical pair. Okay. It is a radical pair means the radicals are maybe formed within the same solvent cage. It may be formed in a different solvent cage. So if it is in the same solvent cage, it is called the geminate pair, and the corresponding recombination is called the geminate recombination, producing your bond and making, I mean, generating the original species back, or maybe a new species formed. Okay. So it is a homolytic cleavage that is responsible for this formation of a triplet. Maybe something else will also happen, that by homolytic cleavage maybe singlet radical pair is also generated, which will undergo intersystem crossing to produce the triplet one. So only difference is that singlet radical pair will have like this one, and triplet one will have this one. But this is not the only description, it has 3 options. 3 options means, I mean, it is a triply degenerate. So therefore, in absence of an external magnetic field, these triply degenerate states are having the same energy. The moment you apply some external field, this degeneracy is lifted, and thereby affecting you know the intersystem crossing process. So here intersystem crossing is happening in a little bit different way. Let's see. So let us look into the radical pairs, spin correlated radical pairs. Okay. There may be uncorrelated radical pairs. We are not interested into that. We are interested into those radical pairs which are having maintaining the correlation. Now, triplet state has three options. Here one is this spin 1, this is spin 2, okay, and it is shown that is the tip of the vector is making a cone. It is just like a funnel. This is another funnel. So, see, both are up. Up means its z projection in the z axis. All these for these two are plus half. So, therefore, it is alpha spin. Okay. So, alpha. So, one spin function is alpha, another spin function is alpha. So, combine for triplet one alpha is one description, in another case it is beta. See, both are down. So, z projection is minus up. Here it is a linear combination of alpha and beta. Okay, it is a linear combination of alpha and beta. Okay, alpha 1 beta 2. Okay, of course, with proper normalization constant. Okay, so so the thing is that this is a linear combination, this is another linear combination. Okay, this is a linear combination alpha plus beta, this is beta minus alpha. Okay, why? Because this is minus, I mean in the reverse sense. So, you see that this is the singlet state, that is the only description, it is a true spin opposed. You see that if you see then it is truly opposed in the sense that these two vectors are exactly opposed to each other, like this, this is your z axis, this is your z axis. Okay, this is your z axis. So, they are these two are exactly opposed. But what happens in case of your triplet? You see, this is your z axis and this is plus up, this is minus up, but it has got a resultant in this direction, and the projection of this resultant on this axis is 0. So, their resultant is not truly 0, but their projection of the resultant on this z axis is 0. That is why it is called T0. So, this is T0, this is T minus, that is both beta, and this is T plus, both alpha, and this is one is beta, another is alpha, of course with they are exactly 180 degree. So, if you view from the top, then for your T plus, okay, so you see that for your T plus, you are viewing from the top. This is for your say S, so this is for T, so T0. So, then it is the other vector, here it is in the same direction. If you view from the top, you have to view from the top. Okay. So, this is a truly spin opposed, therefore, it is singlet. Now, the question is how this singlet to triplet transition is happening. Now, I guess all of you know that molecules, when a radical, I mean a dot is created at some point of some portion of your molecule, then that dot is experiencing some internal magnetic field. Okay, some internal magnetic field, and that in presence of that an internal magnetic field, in absence of the magnetic field, they are oriented randomly. Okay. But the moment your external field is applied, then the spins are going to, I mean they start precessing about that axis like this, like this. I mean this is your axis, it is precessing like this, like this, it is precessing. Okay. Now, this precessional frequency is very much dependent on the magnetic field it is experiencing. Okay. So, the question is, you can I mean the phase difference here for this one, phase difference is 0, you see, red and black both are having the same angle. I mean if you count this angle, then both are having the same angle, and here they are, I mean angle was there 180 degree apart. Okay. So, they are in phase, they are opposed. Okay. Their phase angle is if it is 0, then it is 180 degree. Here both of them are either 0 or 180. So, how can you get this picture from here to here or from here to here? If they maintain a constant phase difference, then what is going to happen, that like say this one, if they maintain a constant phase difference, they will do like this. For this one they will do like this, if they maintain a constant phase difference like this. Okay. They will do like this, and in other case for this one they will do like this. Okay. They will do like this. Okay. So, what is happening, that suppose by some means, if you can increase the precessional frequency of one of these two spins, then there will be dephasing, that is maybe this red will move a little faster than this one. So, at one point of time this red will merge on this. So, red will merge on this, means you are getting this picture. So, that means the merged red on black is basically triplet. So, basically you have got a transition from singlet to triplet 0. Okay. Or vice versa, that such that if black is moving faster than red, then you may get a picture of this, and that is called a singlet. So, in this way, if you can change the relative precessional frequency, okay, then then you can shift from T0 to S or S to T0. Okay. So, that is one way of transforming the system from from T0 to S. Now, how can you get this from T0 to T minus to T0? So, that will require flipping, of this beta spin to alpha spin. That means you need to change this one to this one. How can that happen? That if you can apply an external magnetic field such that this external magnetic field is perpendicular to your internal magnetic field, or maybe there is an external there is another magnetic field which is operative in this direction. So, this is your original space fixed axis, but maybe some internal field is there, or maybe something else that we are not concerned right now. So, suppose that is your this one is your additional field. So, and that field is very close to your beta spin over here. Okay, so that this additional field starts the precession of this beta 1 along this axis. So, this will do like this. Okay. In doing so, what is happening, that let us draw another picture. In doing so, that originally it was like this. This is a beta spin, this is another beta spin. Okay, you are having this extra, I mean additional magnetic field which will start the precession. This is your beta 1, this is beta 2. So, it will start precession around this axis, so that this tip of the vector is now here because of this precession. Okay. So, ultimately what you are getting, this plus this. Okay. So, your picture now becomes this one and that one, and you try to match. This is nothing but your T 0. Okay. This is your external, I mean space fixed axis. So, that means because of this additional precession, that means you need to change the angular momentum. So, that is compensated by the additional field, okay, compensated by the second field. So, there is a conservation of angular momentum has been done in this way. So, it is nothing but a transition from T0 to T minus or T minus to T0. In the same way, you can have transition from T plus to T0, okay, T plus to T0. So, basically what is happening that so you energy level wise you have, say this is your singlet, okay, S, and this is your T. Okay, this is a T. Of course, it has got three levels. So, in absence of any external magnetic field, there is a transition between singlet and triplet. Okay. Now, what you do, you apply your external magnetic field H or E, I mean B is the external magnetic, B is not equal to 0. So, what is going to happen then? Then this triplet becomes like this, and depending on the strength of the external magnetic field, this splitting will change with external magnetic field strength. So, now what is happening, that energetically these two are same, but these two are different. So, transition from this 2 is now getting reduced because of the energy gap factor, because energy gap is there. So, this gap is dependent on this splitting is dependent on your external magnetic field. So, 2/3 of the total population. So, this is 1/3, this is 1/3, this is 1/3. So, these two-thirds of the total triplet population cannot now get converted to singlet. So, what is happening? That they will not recombine. Recombine means say R H, say dot plus say another R dot. So, recombination means maybe say R prime, say R plus R dot H. So, this is your back hydrogen transfer or maybe recombination. So, it will happen, they will not recombine. Only 1/3 of the total triplet population may communicate with singlet and hereby go to singlet and recombine. And here what they will do, when the system is in the triplet state, what they will do? They will simply escape. If the system is in triplet, they will have the least tendency to recombine. I mean, because of their spin arrangement, you see, unless they are like this, I mean these spins are like this, they will not form a bond. Therefore, whenever whenever the system is in triplet state, they will recombine, I mean they will separate out, producing free radicals. But when they are in singlet state, they will quickly recombine to form a bond. Okay. So that is, it is written as escape. So it is not simply cage escape or escape, and here it will recombine. So what will happen? So when there is no external magnetic field, these triplets could have the option to move to singlet, or it may escape. But since this channel is channel producing recombination product, therefore recombination is expected, more recombination may be expected, because it is a very fast process. But when you apply external magnetic field, what is going on? When there is an external magnetic field, then 2/3 of the total population is now here, one third is here, another 1/3 is here. So they are energy wise more compared to this singlet and T0. Therefore their option is only to escape, producing cage escape products. That is, radical pairs are now separated out, and they will no longer recombine, because they will now become a part of different maybe cage. Okay, so it will be very difficult for them to recombine. Okay, or maybe they will recombine, but that is not something what is happening for your correlated radical pairs. So those are becoming uncorrelated radical pairs when they are away from bonding distance of the say of the order of 8 to 10 angstrom. More than that, then there is no roughly, I mean there is no interaction between them. So they will remain as free radicals. So that is why when you take the signal from look into the signal from the oscilloscope, you will be seeing that if it is a truly 100% recombination, then this is your 0 axis, I mean 0 of y axis. So so this will go very close to 0 of y axis. But if there is a fraction that is not undergo full recombination, then what is happening, that it may happen, but maybe there is some residual signal. So this corresponds to your escape products. Okay. So what experimental observation we may expect here, that in presence of external magnetic field, if it is a singlet bond radical pair, what is going to happen? Singlet bond radical pair and triplet bond radical pair will behave in opposite fashion. Okay. So singlet bond radical pair, immediately after its birth, it will tend to recombine. Okay. But if it is a triplet bond, it will not recombine immediately after its birth. It will have to recombine by transferring from triplet state to the singlet. So it will recombine through this. So any hindrance in this path will reduce recombination. Okay. So the same way will reduce recombination for triplet, but for singlet, if there is a hindrance, then we may expect more recombination, because this channel is off. I mean, because of magnetic field, maybe 2/3 of the total population, I mean 2/3 of the, I mean out of 3, 2 channels are off because of external field. Therefore, maybe 1/3 has the option to escape. So that means escape products will be reduced when it is a singlet bond radical pair. So for singlet bond radical pair, in absence of an external magnetic field, if your profile is like this, maybe you can expect like this in presence of B not equal to 0, B. For your triplet bond, if it is like this, maybe you can expect, and maybe with increasing magnetic field it will be like this, B increasing. B increasing. Okay. These are signal, maybe OD or similar quantities, and it is T. Okay. Reverse may be expected, for singlet bond radical pair. Okay. So, that means you have got this energy level diagram. In absence of external magnetic field, you apply B not equal to 0, then you have this option, T0, T plus, T minus, and this is your S. So, this channel remains open, and depending on the field strength, these channels are progressively blocked. Okay. These channels are progressively blocked. So, 2/3 of the population in the triplet state cannot recombine. Okay. That is why for triplet bond radical pair, here you see this escape yield is increasing, because majority of your radicals, I mean 2/3, about 66%, 66% cannot come to singlet state, singlet radical pair. Therefore, this escape yield is increasing. Okay. And this has been found to happen with, say, benzophenone, maybe benzyl, and similar hydrogen for similar hydrogen abstraction reactions. Okay. Benzophenone or benzyl in micellized medium. Micellized medium. Okay. But in other case, if you take this if you take neat solvent, say for benzophenone, do you expect any magnetic field effect? The answer is magnetic field effect is very feebly seen, or maybe sometime you cannot detect any magnetic field effect. Why it is so? Because micelles provide, say this is your micelle, micelles provide, suppose your radical pair is generated, say R1, R2, generated over here. Okay. The moment it is generated, if it is a neat solvent, they have the option maybe to come close, or maybe these have the option to go away. So, once they go away, then it is very difficult for them to come back. There must be some boundary which resists them to separate apart. Okay. So, micelles rather provide such an environment, this micro heterogeneous medium. It is a combination, I mean it is an aggregate of surfactant molecules. So, what is going on, that the moment it is generated, they will try to go this way or maybe come close to each other, but those which are going this way will be reflected. So, reflected by this boundary. So, these micelles, it is basically they are providing reflective boundary, so that these radical pairs will stay for sufficient time, allowing this spin evolution to take place. Okay. Of course, these micelles have opening, I mean small opening, so that the radicals can escape, that happens, but most of the radicals will tend to will tend to remain within this micro cage, so that the spin evolution can take place. Spin evolution can take place means, as I mentioned, that is singlet, I mean singlet to triplet or triplet to singlet evolution. Okay. And of course, it depends on the distance also, that when they are very far apart, then there is virtually no interaction. So, above 10 angstrom there is no virtual interaction, but if it is within 10 angstrom, then singlet and triplet will follow different potential energy curve. Okay. So, and if a system falls, I mean if a radical pair is in the singlet state, then option is recombination. If it is in the triplet state, option is the cage escape. Okay. Now, how to prove that these radicals, I mean these radicals for this radical pair spin chemistry, how to prove that these micelles provide reflective boundary for the enhancement of this magnetokinetic phenomena. Okay. Now, in one case the experience is that if you do the experiments in neat medium, then it is very difficult to see, any magnetic field effect. So, magnetic field effect, if it is there at all, it becomes very feeble. Okay. So, how to look into the actual role of your micelle? It is very simple, that if you make some mixed micelle, okay, or maybe if you can modify the micelle such that its reflectivity is reduced and its this openings are increased, then what is going to happen? So, that can be done by using secondary additives like dioxane or similar small molecules, that these dioxane or other similar molecules form mixed micelle. Okay. So, if they form mixed micelle, then micellar escape rate is increased, because the openings are increased. So, escape rate is increased means you will expect more of escape product rather than the cage product. Cage product means recombination. So, your profile is, in absence of this dioxane and in presence of dioxane, you will be seeing that dioxane increases this cage escape, and sometime it has been found that magnetic field effect is also reduced. The extent of this signal, this time magnetic field effect is reduced. So, that means by formation of a mixed micelle, the cage escape rate is increased, and thereby magnetic field effect is reduced. Okay. So, that is why for observation of your magnetic field effect, it is more important if you can micellize your radical pair within a micelle, because micelles provide a reflective boundary. So, it is a very interesting thing that this singlet to triplet intersystem crossing, although in case of molecular system it is not the molecular triplet, you must remember that, say suppose we have got a molecule, say having a fluorophore, that ground state is singlet, first excited state is also singlet, and maybe there is a triplet state T1. So, what is happening? When you shine, it absorbs light, goes to singlet, and then from singlet it moves to triplet depending on spin orbit coupling. Okay. So, when spin orbit coupling is high, then possibility of this transition is more. because of spin orbit coupling, possibility is more. Okay. So what is going on, that for this transition, this type of molecular singlet triplet transition, you do not expect any any external effect of an external magnetic field. But when it is the question of molecular, not the question of molecular triplet, but when it is the question of radical pair triplet or radical pair singlet, in that case you can expect magnetic field effect. Okay. Sometimes it is referred to as the molecular magnetization, that is, these molecules, I mean radical pairs, they behave like tiny magnets, and in presence of external magnetic field, their spin orientations will change, and as a result of which the relative population of one state is changing with respect to the other state, and thereby you see some nice observations. Okay. So referring to this vector atom model or vector model of electron spin, we have seen that see, this is your 2 alpha spin up, here 2 beta spin down, and this is a combination of alpha and beta. So, and transition from this whole ensemble from here to here is possible by internal field driven, it may be possible, or maybe external field driven as well. When there is no external field, then maybe these 2 and these 3 can freely transfer from here to here, but how much it will transfer, that depends on how fast this state is transferred to this state. Okay. Sometimes it may be very slow process, that singlet to triplet transition is slow, and even in absence of an external field, but when field is applied, that may be that transition from singlet to triplet may get affected. Okay. So so importantly, so what do we get out of it, that that spin chemistry is a new branch of chemistry where we deal with spins. Okay. When it is the question of spin and when it is the question of radical pair mechanism, this mechanism is called the radical pair mechanism. It is a well established mechanism that radical pairs will form either a singlet or maybe a triplet, or sometime it is interesting to note that maybe it's a mixture of singlet and triplet. Okay, it's a strange mixture of singlet and triplet. So in that case, the situation is further complicated, which I am not going to discuss in detail, but just I wanted to give you a flavor of what is going on in this with this spins on molecular levels. Okay. So what is important, that spin chemistry is a very important branch of chemistry. Okay. That a lot of research work, I mean maybe many papers are published there which deals with effect of external magnetic field on radical pair, dynamic behavior of radical pair recombination. Okay. So by applying external magnetic field, you can in principle alter the reaction rate. Why I am talking about reaction rate? Because our main projection for this series of lectures is kinetics. So we have talked about if various external factors that affect the kinetics of a process, like temperature, maybe pressure. Okay. So these are the temperature, pressure, like increasing temperature rate is increased, but external factor like ionic strength is also known to affect this ionic reaction rates. Okay. Like these factors, magnetic field is another factor which I have shown to you that it can also affect the chemical reaction. Okay. That if you think of a radical reaction, suppose a reaction which occurs by radical mechanism. Okay. When it occurs by radical mechanism, and if you know similar things happen, like say a pair of radicals, they maintain spin correlation, then this spin correlation maybe means for this correlated spins, if you apply external magnetic field, then maybe triplet manifold is degeneracy of the triplet manifold is lifted, and thereby recombination tendency or maybe just escape tendency is altered. Okay. So, altered means you expect maybe some different result, different product, or maybe amount, yield of product is reduced maybe. Okay. So, in that respect, it's an important field. It's an important field, and maybe various it has been found for various reactions like like this hydrogen atom transfer reaction, maybe electron transfer reaction. Okay. Where especially for micellized radical pairs, we expect effect of an external magnetic field. So, therefore, we can say that by applying external magnetic field, not only like pressure, temperature, maybe ionic strength, or maybe changing the solvent, but external factors like magnetic field is has been shown to be very effective in changing the overall rate. That is what it is doing is that it alters the singlet triplet interconversion rate. Okay, singlet triplet radical pair, singlet triplet interconversion rate. So, if this interconversion rate is altered, and that singlet radical pair generates cage product or recombination product, and triplet radical product pair will generate escape product. Okay. So, therefore, application of magnetic field will alter the singlet and triplet population, or maybe interconversion between them, and thereby overall reaction is affected. Okay. So, this embodies a nice demonstration that magnetic field effect, although it is not you are applying magnetic field from a distant place, but it is affecting your process, not for all reactions, but reactions those are via radical pairs. Okay. And for micellized radical pairs, it has been found that this effect is magnified, because micelles provide a reflective boundary that the radical pairs are required, that is, a round trip excursion of the radical pair is necessary for their recombination, because micellar cage provides a possibility for recombination. If there is no cage, they will always escape, but when there is a boundary, these radical pairs will get reflected from the boundary and then will have the option to come close, and if they are with proper spin orientation, they will recombine. Okay. So, by the use of vector atom model, we have been able to give you some idea. We try to give you some idea of the spin chemistry, that is the chemistry going on with spins. Okay. Because it is a more detailed description, because spins are responsible for the formation of bond, or maybe cleavage of bond. So we are in the deeper side. Okay. So if you want to know more on this spin chemistry and recent developments, you can visit Nicholas J. Turo's website. Okay, he is in the Columbia University Chemistry Department. So, and there is a popular text by Nicholas J. Turo is also available in the market. You can or maybe in the library you can go through that to get more examples, more more points, or maybe recent advances, more new results. Okay. So this spin chemistry, description of spin chemistry, is as a part of application of flash photolysis, because flash photolysis technique we use to study. Okay. So flash photolysis technique means you just do flash photolysis in presence of an external magnetic field. That's what what we need. Okay. And generally the time scale is nanosecond to microsecond, time scale of observation of the process, of the observation of the phenomena. So that's all about a brief. This is basically nothing but a brief introduction of spin chemistry. We are not going to go into details of it. Okay, because it is a broadly it is a kinetics class. So this completes the fast reaction techniques and its application. So in the next lecture we will focus onto various reactions, especially that are occurring in solution phase, maybe some diffusion control reaction, maybe hydration, factors affecting hydration, etc. So till then, have nice time. Thank you.